All right. So like I said, we're going to start energy and momentum of rigid bodies. Today we're going to cover really just energy concepts. This builds a lot on what we've already done before. We're now just applying it to rigid bodies. We'll start off with kinetic energy, then we'll do work done by forces where we'll see potential energy, and we'll also do non-conservative forces. And then we'll look at conservation of energy. And we should end before there. And if we get through everything, then we'll end early. Okay, so we're going to consider a generic rigid body, shown here undergoing plane motion. I'll draw on the center of mass here. It's going to have some velocity acting at that center of mass. Let's say that's VC. And then some angular velocity, which we'll just say is omega. Since this is planar motion, omega is just equal to theta dot in the k hat direction. We are going to then consider, well, first of all, we're going to prescribe that this rigid body has some mass m and a moment of inertia I. And those are, well, the moment of inertia is about the center of mass, so we can add a little c here. Let me rewrite that m and ic, and those are just general properties of the rigid body. We're going to consider then an infinitesimal point of mass. We'll say this is m sub I, where I is an index here. And that little particle infinitesimal point is going to have a velocity vi. And it will have a position measured from the center of mass, or a relative position, or relative to the center of mass of Ri. And then given this, we can write then that the total kinetic energy is going to be, we're going to use T again, it's going to be equal to 1/2 times the summation from I equals 1 to n of mi times the velocity vi dotted with itself. And that's just what we saw in terms of kinetic energy for particles, although now we're summing over the entire body itself. And if we wanted, we could take a limit of this and turn this into an integral, but there's no need at this point. There's no need at this level in terms of dynamics. Okay, from rigid body kinematics, we can write that VI is going to be equal to the velocity of the center of mass, VC, plus omega crossed with Ri. And that's just the general form relating to the velocity of one point to the velocity of another point and the rotation of the rigid body. We can substitute this in to our kinetic energy in equation 1, and then we're going to get here 1/2 m VC dotted with itself. So that's our translational kinetic energy of the center of mass. Plus, and there's no summation there because it acts purely at the center of mass, plus 1/2 times the summation from I equals 1 to n of mi times the quantity omega crossed with Ri dotted with itself. So another omega cross Ri. Okay, so we're in planar motion, so omega is always equal to some constant or scalar, in this case omega, in the k-hat direction. And we can expand Ri into some generic component in the I direction and a generic component in the J direction. In this case, we will get here that we're going to get omega k-hat crossed with the quantity Ai, A sub I in the I direction plus V sub I in the J direction. That dotted with itself. So omega k-hat crossed with A sub I in the I direction plus B sub I in the J direction. You can carry out these cross products and then you'll get A sub I omega in the J hat direction minus B sub I omega in the I hat direction. And again, dotted with itself. So A sub I times omega in the J hat direction minus B sub I omega in the I hat direction. And then this is going to be equal to the quantity Ai omega squared minus, or actually plus, quantity B sub I times omega in this quantity squared, which is then equal to omega squared times A sub I squared plus B sub I squared. And then this is equal to, I'm going to write it down here. This becomes equal to omega squared times the quantity R sub I dotted with itself. All right, from there, we can substitute that into our kinetic energy, which is going to be 1/2 m VC dot, VC dotted with itself. That's our translational kinetic energy about the center of mass, or of the center of mass, plus 1/2 omega squared times the summation from I equals 1 to n of mi times ri dotted with ri. Okay, this summation here, this is the mass moment of inertia. About the center of mass, which we said earlier is IC. That is a general definition of the mass moment of inertia. Typically, we will consider infinitesimal points, and then you end up having to do integrals in order to compute mass moment of inertia. We're not going to get into the integral part here. We're just going to leave it as this summation. And then we can write that the kinetic energy is equal to 1/2 m times the velocity of center of mass dotted with itself plus 1/2 times IC omega squared. And that is our total kinetic energy. Where the first part is a translational component. Second part is from rotation. Okay, so if a rigid body rotates about some point other than the center of mass, then in general you want to use parallel axis theorem to try and find the right moment of inertia. If the body rotates about a fixed point, then you have two choices. You can either use this general formula on equation 7, and then you bake, and we'll see that in an example, and it automatically takes into account parallel axis theorem, or you can just apply parallel axis theorem. And in that case, what you'll find is that the kinetic energy will be equal to 1/2 I0 I0 here, where that's just the moment of inertia about the pinned position or the fixed point times omega squared. Where here, this I sub O is equal to I sub C, or the moment of inertia about the center of mass, plus the mass times the distance from the center of mass to that fixed position or that pinpoint, which is just parallel axis theorem. All right, any questions on kinetic energy? All right, in that case, we will move on to the work done by a force, which is where we'll deal with kinetic or potential energy, and then also work done by non-conservative forces. So in general, the work done by forces is the same as in particles. But now we have to deal with moments as well, and moments will also produce work. So the work done by a force, we'll just write W sub F here is still equal to the integral from position R1 to position R2 of whatever that force vector is, dotted with dr. That's just the general definition of work done by a force. For the work done by moments, in this case, it's going to be equal to the integral from some angular position to another angular position of that moment dotted with d theta. And everything here is going to be in the k direction, so this will end up just being a scalar integral for us. In 3D, it can get more complicated, but in planar rigid body dynamics, it's, all of the rotations happen about the k direction, or whatever direction is normal to your plane. All right, so just like with particles, conservative forces are going to give rise to potential energy, meaning that they're going to be elements that store energy and then release that energy. Non-conservative forces are going to, they're just going to generate work. External forces will typically inject energy into the system, meaning it's going to increase the energy over time. Dissipative forces are going to do the opposite. They're going to remove energy from the system over time. Okay, we're going to go through some potential energies here. Some of these we've seen before. Some of these will be a little bit different than what we've seen before, and we'll also introduce rotational components as well. Okay, we'll start with translational springs here. So we'll have a spring acting here. I'm just going to measure its position x of t, y of t. In general, this potential energy is still going to be equal to 1/2 k delta squared. That spring stiffness is k. And then here, this delta is a change in length. Or the relative displacement across the spring. So for the spring shown here, delta of t is equal to y of t minus x of t. And so the potential energy is just equal to 1/2 k times y minus x, this quantity squared. So what really changes for us with translational springs is that now these things can be placed not necessarily at the center of mass. Then we've got to deal with the kinematics to determine the motion or the displacement of wherever that spring connects to. The springs themselves act the same. It's really the kinematics of determining what the displacement of each connection point of a spring is, or each end of a spring. All right, we can now also introduce torsional springs. These are just springs that have force that's proportional to rotation. So we'll represent a torsional spring with a spiral. We're going to say that it has a spring stiffness K sub t. That sub t means for torsion. We'll measure the rotation of this inside point. We'll call that theta 1. And then this outside point, we have some rotation. We'll call that theta 2. And then the force produced by a torsional spring is going to be equal to kt times theta 2, quantity theta 2 minus theta 1. Then the potential energy is going to be equal to 1/2 kt times quantity theta 2 minus theta 1, that quantity squared. Yeah, so in general, torsional springs are going to depend about the rotation of the rigid body itself, about the center mass, or if it's rotating about a fixed point, then it's going to depend on the rotation of that fixed point. And what that means is that the position of this torsional spring on the body does not matter specifically. It does not matter where you put it. What matters is the rotation of the location where you put it. And since we're dealing with rigid bodies here, the rotation is the same across the entire rigid body. This is not true when you consider flexible bodies. Then you get local rotations, but not this class. This class, we only deal with rigid bodies. Okay. Move on to gravitational potential energy. In general, this is just going to have the same form as what we saw for particles. Vg is equal to the same thing, mgh. But h is generally measured from the center of mass. Or if you have a compound rigid body, you can either use the center of mass, or you can track the potential energy of each component. And we'll see an example after we go through how do you find the center of mass. And in that example, I'll also show you that you can use parallel axis theorem, or you can use the general formula for kinetic energy to find the kinetic energy. Okay, so we're going to go just through an aside here about how do you find the center of mass if you have some compound rigid body in general. First thing we're going to do is we're going to define an origin and a coordinate system. Really, we're choosing an inertial reference frame. We want the coordinate system because we're going to need to determine position vectors for every subcomponent of our compound rigid body. And that actually is step 2. So we're going to determine position vectors for each component. So again, we need to do kinematics. We do kinematics of pretty much everything in this class. And then from here, we actually have everything we need. And we can define the center of mass. Center of mass is equal to, we use R sub C for that position vector, is equal to the fraction where we have the summation of the mass of each component times the position of each component divided by the total mass, or the sum of the individual mass of the components. So center of mass is really, in a sense, a mass-scaled position vector. Okay. All right, we're just take a look at a very brief example. We're going to look at this rod with a point mass at its tip. In this case, this rod has a length of 2L, and point mass is acting at the right end. The rod has a mass of M, point mass has a mass of 2M. And here we are looking at trying to find the center of mass, or XC here, which I've already gone and drawn. In this case, we can just write this as XC. This is equal to, so the mass of the rod has a center of mass at its center, or just L, so that's going to be M times L, plus for the point mass, it's going to be 2M times 2L. So baked into this, I've put an origin at the right end of this rod, and then you use standard Cartesian for this system. So because the center of mass is a property of the system, it's not going to change as the structure moves, meaning that you can find it in a static configuration, or whatever configuration gives you the simplest coordinate system to compute this center of mass. And then this is divided by the total mass, which is a 2M plus 2M. And then this becomes ML plus 4ML over 3M, which is then equal to 5 over 3L. So then, for this rigid body, which I'm just going to abbreviate as RB. The moment of inertia is, we'll just write I is equal to first ml squared over 12. This is the moment of inertia for the rod about its center of mass. Plus m times xc minus L. That quantity squared. And then this is parallel axis theorem for the rod. And then lastly, for the point mass, we're going to get 2m times quantity 2L minus xc, this quantity squared. And that's our parallel axis theorem for that point mass. Okay, that's the end of our side. We're going to take a look at an example now. In this case, we have a rod with a point mass again. In this case, it is pinned at the left end. Rod has a length of L. There's a torsional spring acting at the pin position, and the rod has mass 2m, point mass has mass m. And there's also a translational spring acting at the point A, shown here. And gravity is also included. Okay, so we're going to compute here first the center mass, the kinetic energy of the system, and we'll do that in two ways. And then we will also compute the potential energy of the system, and we'll also do gravity, potential energy with respect to gravity in two ways. For springs, they're always the same. There's no separate way to do those. All right. Okay, so for A, we're going to do exactly what we just did. We're going to do xc here is equal to 2m times L over 2 plus ml. So that is center mass position for first for the rod, and then second for the point mass, and then divided by total mass, 2m plus m. And in this case, this will be equal to 2ml over 3m, such that our center mass location is 2 over 3 L. Xc is equal to 2 over 3L. And in terms of a position vector, this is going to be 2 over 3L in the E hat R direction using polar coordinates. Okay, Okay, so for kinetic energy, we have two options. We can either directly use parallel axis theorem and find a mass moment of inertia, and then just use rotational kinetic energy, or we can use the general formula, which we're going to deal with the moment of inertia way or parallel axis theorem way, and then we'll deal with the general formula, and we'll show how parallel axis theorem is baked into that general formula. Okay, so let's just say here the kinetic energy is equal to 1/2 I theta dot squared. And what we need to find here is our moment of inertia, I. So this is going to be equal to, first, the mass moment inertia of the rod with respect to its center of mass. This is equal to 2m L squared divided by 12. Then parallel axis theorem applied to from the center of mass of the rod to the pin position, which is the distance of L over 2. So the 2 mL squared divided by 4. Plus the moment of inertia of the point mass, which is this mL squared. And then you sum all these up, you'll find that this is equal to 5 over 3 mL squared. So then our kinetic energy T is going to be equal to 1/2 5 over 3 mL squared times theta dot squared, or kinetic energy is equal to 5 over 6 mL squared theta dot squared. Alternatively, you can write that the kinetic energy T is equal to 1/2 mass of our rod times R sub R dot. So that is the velocity of the center mass of the rod by itself, not considering that point mass, plus 1/2 mass of that point mass times the velocity of the point mass dotted with itself. Since it's a point mass, it has no moment of inertia that we care about. So then plus 1/2 IC for that rod, theta dot squared. Okay, so this RR, this is going to be equal to L over 2 theta dot E hat theta. We're using polar coordinates here. I skipped all of that kinematics. For the point mass, R dot P, it's going to be equal to L theta dot E hat theta. And then our potential or kinetic energy T is going to be equal to 1/2 times 2m times L squared over 4 theta dot squared plus 1/2 mL squared theta dot squared plus 1/2 2mL squared over 12 theta dot squared. So this first term here is translational kinetic energy for just the rod by itself. This middle term is the translational kinetic energy for the particle, or for that point mass. And then lastly, this is the rotational kinetic energy for the rod by itself, ignoring that it's pinned. So this then becomes T is equal to 1/2 mL squared theta dot squared times fraction 2 over 4 plus 1 plus 2 over 12, such that our kinetic energy is equal to 5 over 6 mL squared theta dot squared, which is exactly what we got above as well, meaning that parallel axis theorem is already built into this.
Can you explain again why the point mass has no rotational kinetic energy?
Because it's not rotating about its center.
So there's no moment mass
No.
moment there.
Well, yeah, it's a point, so no, it cannot have any rotation. That's what I'm saying. And for a sphere, the center of rotation would be the center of that point, but it's not like this thing is spinning around about that point. That's what's happening here. Okay. We can also find the kinetic energy from this center mass of the compound system as well. In that case, we can also say that kinetic energy is equal to 1/2 times the total mass, 3m, times the translational or velocity of the center of mass dotted with itself, plus 1/2 times the moment of inertia of the compound mass, or the total rigid body. We'll just call this ICT for the total, theta dot squared. In this case, RC dot is equal to, I think we said 2/3 L. So this is 2/3 L theta dot in the E hat theta direction. For ICT, that we actually had to find. ICT is going to first be one moment here. So we start with moment of inertia for the rod, ignoring the point mass, plus parallel axis theorem for the rod, 2m times quantity 2 over 3L, center of mass, minus L over 2, that quantity squared, And then also we need a parallel axis theorem for the point mass. That's going to be 2L over 3 minus L over 3, which will just give us L over 3, that quantity squared. And so this comes out to be, it ends up being ml squared over 3. This is about the center of mass, this XC position here, not about the pin position. So then kinetic energy, T becomes 1/2 3m times 4/9 theta dot, oops, I left out the L, L squared, theta dot squared, plus 1/2 ml squared over 3 times theta dot squared, 1/2 ml squared theta dot squared, and then we get 4/9. Oh wait, sorry, that should be 12/9. So we have 3 times 4 plus 1/3 this ends up being equal to 1/2 ml squared theta dot squared times 15/9, which lo and behold is 5/3, such that again we find this kinetic energy is 5/6 ml squared theta dot squared. Okay, I had to add an extra page to the notes because, for one, the second way I solved that this morning right before class, and then this third way I solved right now while you guys were working on part 2. So I've added an extra page of notes. I apologize for you not having enough space if you don't, but we shall move on. So that's 3 ways to find the kinetic energy. Part C, we're going to look at potential energies here. I'm going to scroll back up here, just look at our system. So we got a torsional spring, we got a translational spring. The torsional spring is relatively simple. It just depends on the rotation of that rigid body. The translational spring is going to depend on that distance A and its vertical displacement of that position. For the springs, we can write here that Vs is equal to 1/2 kT times theta squared. One point of that torsional spring is connected to the rigid body, another point is connected to the ground. So there's no relative motion, it's just motion caused by theta. And then for the translational spring, this will be 1/2 K times A squared sine squared theta. These are all things we've seen before. Well, not the torsional spring, but at least for the translational spring. For the gravitational potential energy, we have 2 options. We can use the center of mass of the compound system, the compound center of mass, or we could use the parts and do it by parts, where we track the potential energy of each part of that rigid body separately. So Vg here for our center of mass is going to be equal to the total mass, 3m times g, times the vertical displacement of the center of mass, which is going to be 2/3, 2/3 L times sine theta. Such that our gravitational potential energy is 2 mg L sine theta. also do it by parts. I'm going to make a little bit of an annotation here. We're just going to say using center mass, and then VG using parts. In this case, for the rod, we're going to have the mass of 2m times g, and then the vertical displacement of center mass is going to be L over 2 sine theta, and then for the point mass, it just has a mass of m, so m times g, and then its vertical displacement is L sine theta. We're going to cancel out these 2's, and then we'll end up with this being equal to 2mg L sine theta, and so as we can see, they are the same. Such that our total potential energy is 1/2 kT theta squared plus 1/2 Ka squared sine squared theta plus 2 mgl sine theta. No. Well, yeah, one is for, this case is for the torsional spring, and lowercase k is for the translational spring. So, I mean, that's the difference. Oh, I'm sorry, I used the lowercase up here. All right. Let me correct this. That's a good question, actually. Yeah, that's just my mistake. Okay, we're going to move on to non-conservative forces. We're going to go through translational dampers. We also have torsional dampers. We look Coulomb friction, and we'll see where that takes us. So for a translational damper, it's going to be the same symbol we've always had, which is some type of piston sitting inside generally a cylinder. This is what it represents. Care about the velocity at each end, so we'll call this x dot, we'll call this side y dot, and we'll give it a coefficient of b. And in general here, the work done by this damper is going to be b times the integral from t1 to t2 of delta dot squared d tau. So that is the relative velocity across the damper, or this will be equal to, for the damper shown here, b times the integral from t1 to t2, in this case y dot minus x dot, this quantity squared, d tau. And the major difference here is that now you've got to do rigid body kinematics to determine what the velocities are at the points where a damper is connected. This is also true when you're applying Newton's laws. Okay, for a torsional damper, And this just depends on the relative angular velocity. For a plane system, we only have one direction for this. In 3D, this can get more complicated. In this general, the force here is equal to B times B sub t times the relative angular velocity theta 2 minus theta 1 dot, theta 2 dot minus theta 1 dot, and the work done is going to be equal to B sub t times the integral from t1 t2 theta 2 dot minus theta 1 dot is quantity squared d tau. Well, I suppose these should actually be t's rather than taus, since we're computing here integrals from t1 to t2 rather from 0 to t. Okay, we're going to do Coulomb friction, rolling without slip, and then we'll do some external forces. So for Coulomb friction, this in general, the work done by friction is going to be mu times the normal force times the integral. This assumes that your normal force does not change with time. If you have a normal force that is changing with time, it goes inside of the integral. So in fact, let me rewrite this and bring this in because we're trying to do a general form here. So it's going to be the integral. Mu is just a constant always. So mu times the integral t1 to t2 of n of t times velocity of center of mass velocity of the contact point, not center of mass, times the signum of Vc, and this is actually just the scalar speed of that contact point, dt, where Vc here is the velocity of the contact point. Okay, so when I said velocity of the contact point, this is the velocity of the contact point tangent to that surface, tangent to that normal vector. Okay, with rolling without slip is a special case. In this case, the contact velocity is 0, meaning that the contact point is not moving or has a 0 velocity, so there's no work produced by friction. So in this case, the contact velocity is 0, so friction produces no work. Friction force produces no work. So in rolling without slip, that is, there is no dissipation due to friction. Friction's entire purpose is to act as a constraint that forces the system to roll without slip. And in general, constrained forces produce no work. All right. Lastly, we're going to do an external applied force. In this case, the work done by some external force, W sub F, is going to be the integral from R1 to R2 of F dotted with the R. This is then equal to the integral from T1 to T2 of F dotted with the velocity R sub F dot dt, where this R vector, RF dot, this is the velocity vector of the location of that applied force, which means that you need to use rigid body kinematics to find this velocity from, if it's not acting at the center of mass, you'll need to implement your velocity formula for finding what that velocity is. Okay, so then we can expand this and we'll get that the work done. Actually, we're going to stop here.